Hello, I'm Francesca Giuliani and I'm presenting a contribution on the conservation and structural diagnosis of ancient city walls. This is a peculiar type of architectural heritage that is widespread in Italy and presents diverse geometrical, material, architectural and structural characteristics. The contribution proposes a novel scan to BIM process that has been applied to a case study in Tuscany, the city walls of Pisa. City walls played a key role in defending people and places from foreign invaders throughout history and have been significant for shaping local cultures. Today, they hold great potential as cultural resources and should be therefore preserved. More than 140 walled cities have been identified and mapped in the region of Tuscany. Despite the differences, they present common issues related to the great extension and dimension, which may hinder the capacity of experts to gather uniform information and data for heritage management. Hence, their analysis requires adapting the conventional workflows in order to obtain results in a reasonable time. Moreover, the large number of monumental constructions spread across a vast territory poses challenges to the effective implementation of the planned preventive conservation, as proven by the many failure events that have recently occurred in diverse sites. These failure events have stressed the need for ensuring systematic, condition and significance-based conservation, repair and maintenance of ancient city walls. This contribution aims to create a suitable decision support system involving the modeling, visualization, compilation, and management of the knowledge of city walls. As such, it aims at experimenting with a rapid and yet accurate workflow for developing heritage building information models, the so-called HBIM, which can strengthen the preventive and planned conservation and disaster risk governance of city walls. The methodology is based on the multidisciplinary and cross-scalar knowledge of the assets that are investigated by applying a novel scan-to-BIM workflow. Diverse data have been acquired to achieve a good knowledge of the assets, starting from historical and documentary data, and then characterizing materials and damage patterns with on-site inspections. Data are processed to derive basic facts and figures of the asset and to annotate significant features regarding its construction technology and actual conditions. Special emphasis is given to the survey and modeling phases. In fact, the proposal entails a fully automated 3D reconstruction of the scene from oriented images by applying structure from motion photogrammetry, which allows for limiting manual operations that are time-consuming and prone to errors. In this way, we can obtain accurate as-built models to which information can be associated by defining fit-for-purpose properties. Further benefits derive from the automation of the information phase, which is ensured by bridging diverse commercial software and tools. A complete description of the proposal will be provided with reference to the case study. The case study presented in this paper concerns a large sector of the city walls of Pisa, a well-preserved fortified system located in Tuscany, in Italy. The walls are a remarkable example of the medieval construction techniques and present peculiar characteristics with slender curtain walls, towers, wide gates and bastions. Although the walls have progressively lost the protective function, they have been preserved and only limited sectors of the perimeters have been lost over the centuries. Today, the overall length of the circuit is approximately 7 kilometers, the average age of the curtain walls is 11 meters, and the thickness is about 2 meters. The circuit has been classified according to the morphological type of element, thus distinguishing the curtain walls, gates, towers, bastions, and fortresses. As shown in the figure, the study has investigated the northeast sector, including 5 curtains, 3 gates, and 3 towers. The structure is made of multi-leaf masonry with 2 brick and stone outer leaves and the inner core of stone and rubble masonry. Despite the heterogeneous appearance of the walls, 7 prevalent material classes have been identified to characterize locally homogeneous areas, showing similar construction techniques. The classes consider the lithology, shape and dimension of blocks, the presence of mortar, and finally their arrangement. The geometrical survey is conducted through photogrammetric techniques combined with topographic measurements to derive the 3D coordinates of several positional data onto the architectural heritage that are used as control points. The application of structure from motion photogrammetry allows for reconstructing the 3D geometry of the scene, starting from a rapid and less demanding data acquisition phase. This method is able to automatically and iteratively solve the positioning and orientation of cameras from a set of many overlapping images without the need to provide a priori a network of targets. Coordinates can be collected with several range-based methods such as laser scanners or more traditional surveying instruments. In this study, the survey employed a total station that provides high-quality and precise coordinates of a series of control points. Besides, the survey exploits remote technologies like global positioning systems, the GPS, in the shooting of photographs in order to improve the alignment and orientation of cameras. Photographs were acquired using an iPhone 11 camera with GPS on. They were taken from the bottom and from the wall walk to capture the asset with a sufficiently good resolution. The distance from the wall ranged between 7 and 12 meters, depending on the accessibility, which was often limited due to the presence of trees, roadways, and fences. Photographs were taken in longitudinal strips, ensuring a high degree of overlap, about 70% on average, and the acquisition was done over several days at different times to have the most uniform illumination possible. Photographs and positional data have been processed with the structure from motion software Agisoft Metashape. The dense crowd of the investigated sector of the city walls is obtained from an overall number of photographs equal to 338 over a total length of approximately 400 meters. The figure shows the investigated portion and some details processed with the software. By applying this methodology, we can achieve a good result in a reasonable time, as shown in the figures. If we compare the granularity of the real photograph A with the point cloud B, the mesh C, and the texture D, we can state that the processed outputs preserve a good level of detail compatible with the large dimension of the object under investigation, as they are able to reproduce the geometric irregularities of the city walls. The textured 3D model can be exported in three-dimensional formats like OBJ or wavefront that guarantees the direct association of the processed texture even in a different software. In this study, the final textured model has been imported in the McNeil Rhinoceros software that is able to easily manage complex geometries and host Grasshopper, an algorithmic modeling environment supporting a wide range of useful plugins. Once we have surveyed and annotated all the significant properties on the orthomosaics of the walls, we can import data in Rhinoceros and use them as projection planes. In the figure, we can see an example concerning construction materials and three simple deterioration patterns, namely alveolization, moisture, and vegetation. The areas corresponding to the materials and deterioration patterns can be used to directly segment the mesh. The projection is fully automated in Grasshopper thanks to the use of the mesh split component that uses the closed 2D entities previously defined in the annotation planes to produce new submeshes associated with different properties. The scan to BIM procedure here proposed employs the Grasshopper plugin ArchiCAD-like connection developed by Graphisoft, which enables the connection with the ArchiCAD software. Specifically, the Grasshopper ArchiCAD-like connection makes it simple to generate native ArchiCAD BIM elements in Grasshopper using familiar nodes, thus automating and simplifying common and complex processes. Texture 3D model can be turned into BIM object using the Morph Solid component, in which we can connect several morph settings and customize the properties. The main advantage of HBIM lies in the possibility to integrate into a single model multiple types of data from diverse documentary sources, inspections, and diagnosis techniques. Diverse type of data can be used to inform the model, such as images, text, numbers, and even attached documents. The customized groups and properties regard several aspects that are relevant for heritage conservation and structural diagnosis, namely the element identification code, the periodization of transformations, historical documentation, stratigraphic analysis, the masonry typologies, which is described by diverse attributes, then past interventions and maintenance plans, criticalities of the context or asset. We organized the new customized properties in ArchiCAD in two groups, namely HBIM identity data and HBIM design parameters related to masonry types. Then we proceeded with connecting the ArchiCAD file with the one in Grasshopper, such that the properties are directly imported in the latter. At the end, when synchronized, any change in one of the two tools is automatically read and imported in the other. Therefore, the HBIM can be easily managed and modified according to the need of the user. The ArchiCAD BIM environment allows for managing the information related to the historical artifact through the setting of graphic override combinations that are defined by specific graphic override rules. The latter produce typed graphic views that depend on the assigned information and allow users to visualize data according to the need. To conclude, this contribution examined ancient city walls and addressed the challenges of creating HBIM models for heritage conservation and structural diagnosis. The study emphasizes the importance of multi-source documentation to achieve a good knowledge of the asset under investigation. An historical, documentary or material source is important to address planned preventive conservation. The workflow stands out for the ability to produce reliable as-built models in an efficient way. In fact, we were able to import complex 3D texture mesh elements in the BIM environment and to compile HBIM information bringing diverse software and tools such as ArchiCAD, Rhinoceros, and Grasshopper. By automating and simplifying common and complex processes, the workflow proposed in this work is capable of ensuring a rapid and yet accurate and reliable result by speeding up the data acquisition and the 3D model creation and information. The overall Scan2BIM procedure has the advantage of being fast, lean, and easily modifiable and customizable. Besides, the workflow ensures great interoperability. In fact, it allows for documenting and recording the characteristic of the building over a complete and sufficiently accurate model, which can be used to track and share data among heritage professionals and digital tools. As such, the proposed framework promotes knowledge-based decision-making driven by comprehensive and updated data. Thank you very much for your attention, and if you have any question, please don't hesitate to contact us.